It's for, yeah, you think there's related? Related.
Really does. I think she's well. I think she's. No.
I think you are. Like,
Alright. You're still playing. Congrats.
Great.
It's not like I can't.
Let's get started today. So again, I'm just repeating the announcement made at the last class that so that nobody misses it. There will be a quiz on Friday. The topics are qubit state and block sphere. Books and close notes, but whatever formulas you want will be on the test. So nobody will. Be roughly 9 or 10 questions with multiple parts. Any questions before I move on? Okay, so the outline for this week is that we'll continue our and finish up learning linear algebra that you need for the course. Most of it is just the math and definitions and understanding how to use them. But at the end, I thought I would finish with an application of linear algebra. So you may remember the quantum bomb detector that we made back a few lectures ago. And I'm going to now revisit it with linear algebra and show how to build a perfect quantum bomb detector. So that's in today's, most likely, I think I'll get to that today. And then on Friday, either before or after the exam, we'll just finish up, we'll start introducing multiple qubits into the course. Okay, so just to recall, okay, so just to recall that the definition of a unitary matrix is one where U dagger, which is the conjugate transpose of the matrix, times U is an identity matrix. And and of course U dagger, so that's both ways, whether I multiply the matrix from the right or the left. And you'll see there are examples, I think maybe the homework that I'll assign you next class is that it does matter the order. So meaning there are some possibilities where dagger times itself may not be the same as my matrix A times its dagger. Okay. So they don't always commute, as we say, quantum mechanics. But yeah, these matrices do commute and they give us U and U dagger, and they give us the identity matrix. Okay, and one powerful statement that we made last time was that all quantum gates have to be unitary matrices to preserve the length or to preserve the normalization of the qubit state. Because any qubit state, after operation by a valid quantum gate, must remain a qubit state and therefore must remain normalized. And that is what actually allowed us to derive this condition in the last class. And to go the other way is that if you can write down a unitary matrix, then it corresponds to some quantum gate. Okay. Okay, now we'll also introduce another concept, which is actually quite familiar because we discussed the classical version of this back in week 2 or something, which is that we say that a gate or a matrix M is reversible or invertible if there exists a matrix M inverse, M to the minus 1 is how we denote it, but it's M inverse such that M inverse times M equals M times M inverse equals the identity matrix. Okay. hopefully this makes sense. It's kind of, intuitive, hopefully. And since a quantum gate is unitary, we see that it satisfies U dagger U equals U dagger equals I. We see that a quantum gate is also always reversible. And its inverse is the same as its Hermitian adjoint, that is the dagger matrix, U dagger. Okay. Therefore, U dagger is kind of like the undo operation on your computer, right? You do something, you don't like it, you undo it right away with U dagger. Okay. So that's what U dagger does. Okay, it's just a definition. And the reason we introduce it is just to say that all classical gates that we can do, that we can write as reversible gates, can immediately be made into quantum gates, right? We already said that before, but now the idea of it becomes a little bit more concrete or mathematical, because any classical reversible gate will have a matrix that we can write down. When we do multiple qubits, we'll see how to write down such matrices. For single qubits, it's, we've already seen some examples, but for multiple qubits, it starts to become a little bit more concrete because you have like a truth table. You can do truth tables just like we did for classical gates. And then we will see that any reversible classical gate can be written as a unitary gate because it's invertible, and if it's all real numbers, then it's also it's yes.
So taking the inverse of a matrix or quantum gate it's the same operation, not the same operation, but it has the same outcome as taking the adjoint of quantum gate.
Yeah, you're absolutely right. So there is a difference. So for normal matrices, finding the matrix is not quite as easy as for unitary matrices. For normal matrices, if you look in any linear algebra textbook, you'll see how they define the operation of taking the inverse. Okay, and if you have done any kind of like linear algebra course or linear programming course, you might have seen that, which is, you have to calculate some cofactor matrices, find the determinant, X, blah, 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 etc. Anyway, that's not important. What the point is, yes, it's much more complicated usually to find the inverse. But for unitary matrices, it's very simple. You just find the dagger, and the dagger, which is conjugate transpose, the adjoint matrix, is the inverse matrix as well. Okay, so that's the nice property of unitary matrices. It's very easy to find their inverse. You got it? Yeah.
So to follow up on that, then you could say that the adjoint of the gate or of the matrix for a gate is equal to the inverse.
Yeah, of the gate. Correct. Absolutely. That's, I think, what I said. Did I not make that clear?
Oh, did I?
Yeah.
I might have missed.
No, yeah, it's here. Inverse is the same as its Hermitian object. That's good. It's good to repeat. Make sure everybody catches it. And in fact, in many cases, the inverse or the Hermitian adjoint of a unitary gate will be itself sometimes. We already seen many examples of that. So you remember the x squared is equal to identity matrix, right? So x times x is an identity matrix. X itself is a unitary matrix. Therefore, x is its own inverse and its own adjoint. Okay. Similarly, y, similarly, z, and h, the Hadamard gate, are all their own adjoints and therefore their own inverses. So if I do Hadamard, we bring back identity, right? You may recall from earlier discussions. So those four basic gates kind of that we introduced are, four, X, Y, Z, and Hadamard, which are the sort of, important gates in quantum computing. They're all their own inverses. Okay. Okay, so now I want to introduce another concept, which is called the outer product, and we'll see in a minute why it's useful. So let's go through it in this step. So first, let's define a state psi, which is A0 plus B1, which we write with our linear algebra notation as a column vector AV. Similarly, we have another state phi, which is this over here, CD, okay, column vector. Then we define an outer product from these two states as follows. We take the ket psi and multiply it by the dual vector phi, or the bra vector phi. And in linear algebra, this has a very straightforward implementation. We say we take the column vector A, B and multiply it by the row vector C star, D star, right? Because that's the dual vector to phi. Okay. You'll see the need for these in a minute, but I'm just introducing it at first. So we multiply. How do we go? What do we do with this product here? Well, we use the rules of linear algebra. Okay, we take this entire column vector, multiply it into C star, and we take this entire column vector and multiply it into D star. Right? That's the rules of linear algebra. Everything is linear. Okay, linear multiplication and addition and so on. So that's our new matrix. And now it's just simple. It's C star times A, C star times B, D star times A, D star times B. So that is this new matrix, which is, so you see that the outer product is always a matrix. So taking a ket and multiplying by a bra of some other vector is always going to give me a matrix, which looks like this. Okay. Now it's not guaranteed that this matrix is unitary yet. Okay, but it's like a sort of, we can think of it as like forming some matrix. Okay. This step clear to everyone? How we find the outer product? So let's do an example. So we define this U as 1, 0 plus 0, 1. Okay. So we know, of course, matrix 0 is 1, 0. And the ket 1 is the column vector 0, 1. So to calculate this, we have 0, 1, which is 1 over here, right? It's over there, and then we have to find the dual for this column vector, which is just the row vector 1, 0, the conjugate of 1, 0. These are all real numbers, so we just write it as 1, 0, row vector. Plus, we have 1, 0 ket, which is this state over here, and then the dual vector to 1, which is 0, 1. Okay. And we can now write this. We can use the rules of linear algebra. Let's find this one. So I need to take this entire vector in here and multiply it out. So that gives me 0 and 1, right? When I take 1 and multiply it into this vector over here, I get 0, 1. And then over here, I get 0, 0. Because 0 multiplying everything. Similarly, over here, I get 0, 0 here because the first element here is 0. And we also get now another matrix, which is 1 multiplying all of this. So that gives me the matrix 1, 0 over here, or the column 1, 0. Everybody see how I did that? Okay. So when I add these two together, I get 0, 1, 1, 0, which, if you look back, is just the X gate. So this is the X operation or the NOT operation. Okay. You can kind of see the action of U on any state 0 using our rules of ket algebra. You know, the ket algebra allows us to calculate, to just almost read off what the action of U will be on any state Of course, we can do any state psi simply by taking U and multiplying by the column vector. So I could do it with matrix algebra, but I can also do it with the Ket algebra as follows. So I write down U. Okay, this is the Ket notation. And then I have 0 outside. Okay. And as I take 0 and propagate it through this operator, right, through this gate, well, 0 inner product with 0 gives me 1. So that's 1 over here. And then 0 inner product with 1 gives me 0, right? So therefore, U operating on 0 gives me 1. So it's a NOT operation. And of course, you can verify for yourself, U acting on 1 gives me 0 as well. Okay. And we can do this, of course, on using the rules of matrix algebra as well. This is a repetition of what we did the first time, but I'm just doing it again. And or maybe a little bit more interesting, or I mean, it's fairly obvious at this point, I hope for you, that if I take now 1, 0, 1, 1, 0, and I act it on any state psi, which is composed of A and B, right? So A and B are the amplitudes. So this is the state psi equals A 0 plus B 1. I can do it again using the rules of Ket algebra, or with this linear algebra, it becomes almost trivial. It's just the BA, right? It flips the A and B in that column. Which also would result if you did it with the linear Ket algebra. Okay, everybody clear on this? How we got this? Any questions? Yeah.
So that expression there.
Yeah.
For the representation of X gate.
Yeah.
How did you figure that out?
I didn't figure it out. I just introduced it here.
Oh.
Yeah. But it's almost like you develop an intuition. You look at the matrix elements for U, the elements of U, and you can almost read them off. If I were to label.
Somebody did a research and.
No, I mean, you can just label them. So for example, if I label all the rows by the column, by the bras, and this by the text, like this. Okay. Then you can see right away that the only non-zero elements are 1 ket and 0 bra. So that's 1 0. You see that 1 and 0, right? And then similarly, this one is ket 0 bra. Ket 0 bra. Okay. Which is exactly what I wrote. I erased it. Oh no, here it is. Ket 1 bra 0 plus ket 0 bra. So if you like, you can think of the rows as being labeled by the bras and the columns as being labeled by the kets, and then you can reconstruct what the ket representation of this matrix must be. Okay, that is that direct product or outer product representation. Is that okay with everyone? Start for a minute, maybe. In fact, the way I think about these matrices is basically the elements, like here. So if I call this element U00, U01, U10, U11, right? Then that just gives me basically this exact same thing. It's the ket 1, the second element is the ket, and the first element is the bra. That helps me to read off what these matrix elements are. So the other way to say that is U01 is the matrix element of 0, U1. So inner product of U acting on 1 with the 0 element. Okay. And same with U10 and U11, etc. If you don't believe me, try it out. Try to take U, act on some ket 1, and then inner product with 0 and verify for yourself that it does give you the right answer. Okay. But if not, you can just ignore all that and use the rules of our linear algebra, which is now erased, but the way we did it. Okay. After a while, you start to get an intuition for what a gate is doing just by reading the Ket algebra representation in this direct product representation. As we get to multiple qubits, this will start to become harder and harder, and eventually we'll just resort to the matrices. But at least for single qubit gates, this gives you a quick way to understand what this gate must be doing. Okay. Any questions? I didn't check for unitarity, but it's pretty straightforward because in that case, the gate was identical to itself when you take the Hermitian adjoint, the adjoint matrix. Because the matrix was 0, 1, 1, 0. So transpose of that is also 0, 1, 1, 0. Right? You just transpose the off diagonal elements, and then taking conjugate of real numbers gives you back the real. So the matrix is identical to itself, which is what I said earlier. The X gate is identical to itself when you take the adjoint, and then so therefore multiplying by itself, we already saw X squared is the identity matrix. So I'm not repeating the steps here. Hopefully you understand this from what I'm saying, like how I. If you don't, again, I encourage you to go back and check these things on your own. The only way to do these things is like the first few times, just repeat everything that I'm doing. Convince yourself that you know how to do it as well before moving on. So now I want to introduce a very important unitary gate, which is the change of basis or rotation gate. Okay. So we have already seen one example of it, sort of, which is where we flip the 0 and 1 operators, right? I mean, we made a state go from being A0 plus B1 to B0 plus A1. We sort of flipped the basis, if you like. We called 0 as 1 and 1 as 0, right? So not operator. Well, we can consider a gate which looks like this. So this gate no longer, you can see it is 0, and then there's a plus over here, which is the plus is our usual 1 over root 2, 0 plus 1 over root 2, 1, the plus x state, and this is the minus x state on the block state. Okay. So let's look at this gate and try to understand what it does. Okay. So before I show you the algebra, I'll just explain what the outcome is. Okay. The outcome is that if I take this rotation gate and operate it on the state 0, I'll get the plus state. Again, you can almost sort of read it up. Okay. And if I take this rotation gate and act on the state 1, I get the minus state. Okay. Okay, let me come back to that in a minute. I wish I could hide this caption. Maybe I have to hide it. It's annoying. Annoying when it's on the screen and I can't see the bottom of the screen. Okay. Yeah, sorry. Where was I? Yeah, okay, so we'll show the algebra of this now. But the result is, do you know what this gate is called? Have you seen a gate which does this already? Takes 0 to plus and 1 to minus. Yes.
The Hadamard gate.
Hadamard gate. Excellent. Thank you. So this gate that I've written here is indeed the Hadamard gate, but written in a very different way than we saw before. You can do it by the rules of Ket algebra, but let's just skip to doing it with linear algebra because it's so much easier, right? If you want, you can verify the Ket algebra as well on your own. It's plus 0 plus minus 1. It almost is telling what it does just by writing it in this Ket language like this, right? You can see it takes 0 and then take it to plus 1 and it'll take it to minus if I sandwich it between a 1 and a plus, right? So it's telling you its action with this language, and now we just have to write it out. So the Ket plus is this column vector 1 over root 2, 1 over root 2, and this is our old friend, the dual vector 0. So we just write that, and this is 1 over root 2 minus 1 over root 2 acting on the state now 0. Okay, again by the definition of the outer product, so we'll get 1 multiplying this whole column vector, so it's 1 over root 2, 1 over 2, and then 0, 0 over here, plus now 0, 0 over here, and 1 over root 2 minus 1. This gives me this new rotation gate. Okay, now let's verify what we said already, which is that R acting on the state plus state R acting on the state 0. What is that? Well, take that matrix. And I operate it on the column vector 1, 0. Okay, so now we have to use the rules of matrix multiplication, right? So 1 over root 2 times 1, 1 over root 2 times 1 plus 1 over root 2 times 0 is 1 over root 2. Okay, and then 1 over root 2 acting on 1, and then minus 1 over root 2 times 0, so that's also 1 over. Okay. And this, of course, is the original plus state that we started. Okay, and okay, I think you can verify for yourself that indeed, same method, you'll get that this is 1 over root 2 and minus 1 over root 2 when I multiply it by the state, the column vector 0, 1. Okay. Okay with this? So now what will be the action on a general state psi? It's just whatever Hadamard would do on a state psi, but what's more interesting is, if I now take a state psi and write it in terms of the column vectors A, B, this is the column vector A, 0 plus B, 1, right? That's what this is in the Ket language, right? And in this language, we've seen R acting on 0 gives me plus, so 0 is equal to R inverse acting on plus, right? But of course, R inverse, as we know, is R dagger. That is, you can think of it as I'm multiplying both sides of this equation by R dagger. Okay, so on the left-hand side, I have R dagger times R, which is the identity matrix. On the right hand, I have R dagger times plus. Okay, so this whole operation psi can be written now as A times R dagger 0 plus B, plus B times R dagger minus, which means that these guys here, A times R dagger and B times R dagger, are nothing but the components of psi in the plus and the minus basis. Okay, which means, of course, we can also write this as the the projection of psi onto plus the projection of psi onto minus. Of course, since R dagger is a unitary and linear matrix, another way to think about it is that the psi prime, which is equal to R dagger psi, is the new representation in the new basis. That is, if I take the R dagger and multiply it by the column vector psi, I'll get a new column vector which represents the components of psi in the new basis plus and minus. Is this step clear to everyone? Essentially, I'm just saying that I replace 0 with R dagger plus, and 1 with R dagger minus. So that's equivalent to R dagger times this new matrix psi prime, or sorry, psi equals R dagger psi prime, right? Whichever. Okay, which way do I want to go? Let me be very clear. So like saying that, let me give a geometrical analogy because I think that sometimes helps. Okay, let me give a geometrical analogy. So imagine that I have some axes, and let's call them, for sake of argument, x and y, but let's call them as 0 and 1. Okay, so this is the 0 and 1 axis on 2 dimensions. Okay, just bear with me for a second. Okay, and now I've rotated with this rotation gate. Okay, to plus and minus by some angle. Okay, let's forget the angle for now, but this rotation gate effectively has taken me into some new basis states. So it's taken 0 to R dagger plus and 1 to R dagger minus. Right, that's what we arrive at over here. Right. So therefore, psi, which is over here, this new thing I'm going to call as the psi prime. Okay. It is the matrix or the column vector psi prime represents the components of the matrix, the state, the same qubit state. So now I also draw some new qubit state. There's some colored chalk over there. Yeah. So originally, let's say I started, before I did anything, let's say I started with in this. So let's start with the state 0, 1. Remember, I've said before, this is 0 and 1. I'm just making an analogy to 2-dimensional vectors that you are all very familiar with, right? So let's say I take the state vector psi over here, which is some linear combination of the basis vectors 0 and 1. Okay. Then I've rotated the basis states to plus and minus, right? Through R, right? So R is like a rotation that takes me rigidly because it preserves, it's a unitary matrix, it preserves all the angles and the lengths and so on, right? That's what a unitary matrix does. Okay. So you can see now this psi now has gone to some psi prime in this new matrix, in this new axis, right? It doesn't have the same components along plus and minus that it did when it was along 0 and 1, clearly, right? Because the angle it makes with plus is smaller, the angle it makes with minus is larger, right? So therefore, from this representation, we see that psi has gone to psi prime. I mean, it's the same psi, it hasn't changed in some sense. The state is the same. It's just its representation, it's the column vector that I would write down for it in this new basis is now different. Okay. And how is it different? Well, I just take R dagger and multiply it into the old psi matrix. Okay. Is that clear to everyone? Or the geometrical analogy at least? Or as I said, you can just remember it from this relationship. So wherever 0 is, I put R dagger plus, 1, I put R dagger minus, and then whatever these components are must be the projection of psi onto plus and the projection of psi onto minus. Okay. And we can verify all this, of course, with Mathematica, for example. So yeah, that's just that statement over there. So again, this is just kind of outlining that intuition that I was just telling you. So that in the new basis, the qubit state is R dagger psi. So we multiply the old column vector by the inverse of the gate to find the new column vector, which I just wrote for you over there. Okay, it's just the same things. I just wrote it down on the PowerPoint. So here is some code. I just show you first in Mathematica. Okay. So I have to define all the kets. Okay, I just use the Mathematica list to create the 0, 1 state, plus, minus. All this is in the slide, so you don't have to you can. But I do encourage you to type it out on your own, just so that you kind of get some experience with these packages. Because it does help to be familiar with at least one of these packages. Okay, and then I define minus state y plus, which instead of calling it I plus, in our textbook I'm following that notation, which is plus I, right? Is the state 1i, but instead I called it y plus because it's also the state along the y-axis. And then y minus, and then we want to define all the corresponding dual vectors as well. So in Mathematica, that's just you just take conjugate transpose and flatten it to make it look like a vector. Other than that, it's exactly the same. And here, I've given you a comment, which is the plus I state and minus I state, the duals. And then I can find using in Mathematica, it's called the Kronecker product, which is the outer product of 0 and bra 0, which is 0, bra 0, right? That is ket 0, bra 0, ket 0, bra 1, ket 1, bra 0, ket 1, bra 1. And now I can show, okay, I'll come back to this relationship in a minute. But so for example, let's take the X gate that I had written down earlier. Ket 1 bra 0 plus ket 0 bra 1, immediately you get indeed the X gate. Okay, 0, 1, 1, 0, which we did also ourselves as well. Okay. And then you can also do Kronecker product of the plus with bra 0 and minus with bra 1, which we also did on the board. Again, we get as expected the result over here. Okay. And again, by multiplying u with, I call it u instead of r, but same thing. Multiplying it by 0, I get 1 over root 2, 1 over root 2, 1 over root 2, minus 1 over root 2 as expected. And then finally, I'm checking for unitarity. Okay. So you just do the multiplication again, take the dagger and multiply them out, and you get identity matrix as expected. And then ignore this for a minute. And then here I'm calculating, I find the dagger, okay, which is conjugate transpose of our operator. And then I find new psi, which is the psi in the new basis, is A times U dagger 0 plus B times U dagger 1, written in matrix form. That gives me A plus B over root 2, A minus B over root 2. And that you would also have gotten if you had expressed 0 in terms of plus and minus and substituted it back into the relationship. So if you don't recall, we did this in an earlier lecture. So going back to here. So if instead of writing it in this fancy notation, oops. Instead of writing it in this fancy notation, if I had just written this as in ket algebra, you know, plus is equal to 1 over root 2, 0 plus 1, and minus equals 1 over root 2, 0 minus 1. And then I had asked you, how do I find 0? What do? How do you find the 0 state in terms of plus and minus? We went through this in a few lectures ago. What should I do to find that? 0 in terms of plus and minus. Yes.
Like add the two to cancel out one.
Exactly. So you add the 2, that cancels out this guy. So that gives me 1 over root 2 plus minus. I skipped a step. When you add those two together, you get 2 divided by root 2 times 0. So that's root 2 times 0. And then I just take it over here. And then similarly, I can find 1 equals 1 over root 2 plus minus. It's very symmetric, the relationship between 0, 1, and plus minus. And now I would have substituted this if I wanted to find psi in terms of any arbitrary psi. Then if I take any arbitrary psi AB, A0 plus B1, well, what would I have to do? I would substitute 0 as 1 over root 2 plus minus, and 1 as 1 over root 2 plus minus. Combine all the terms with plus, I'll get A plus B divided by root 2 in terms of plus, and A minus B divided by root 2 in terms of the in front of the minus here, right? So that's exactly what I've just gotten by taking this rotation gate and multiplying it into the state size. So it's a one step, once I have the rotation gate, it's just a one step process to find the components along any other direction. Is that clear what I'm talking about? It's the same thing, but now we're casting it into linear algebra, which avoids having to solve like this for plus and minus. What if it's something more complicated? Some arbitrary state A, alpha beta, which is some I times root 3 over 2 plus minus e to the I pi over 5, 0. Now suddenly you're like, oh, what do I have to multiply by to like find this thing? But now I make it, mechanical. I just write down the matrix, find the matrix, and then after that you can let Mathematica or Python do the hard work. Not the hard, the easy, the calculation, which to be honest, I mess that up all the time. So it's certainly understandable that we don't want to rely on our own arithmetical accuracies. Okay, so that is the same result. So A over root 2 plus B over root 2, A over root 2 minus B over root 2. So this is Mathematica. And you can do the same in Python now. As I've told you before, in Python, the problem is that symbolic stuff is not quite as easy. So instead of writing psi as A and B, I will write psi as some numbers, just so I can. So it's a little bit, tricky. But okay, here's the code. Again, it's going to be in your. I defined the dual vectors, but it turns out with NumPy you don't really need the dual vectors because NumPy knows outer products already. So you can just use the NumPy outer product, which I'll show you in a minute. So again, just to back up, here are all the same definitions, same basis states, just defined in NumPy language, NumPy code, and then I just go through. So that's just the way of defining the duals. But as I said, you can define it either using something called the Kronecker product. Again, I encourage you to go back if you're a Python person and just look up the definitions of all of these functions in NumPy, or you use the outer product. And the outer product just is 0, 0, gives me catch 0 browsing automatically. Okay. Same with all of these. Okay, and then I can work through. Again, I'm just jumping straight to the X gate. X gate is just that 0, 1, 1, 0 as we expect. And then I can do the change of basis to the plus minus states. So I call that the R gate. And then I take again outer product of plus with 0, outer product of minus with 1. And then I get the same matrix that we've been working with. And again, if I want to find what it does to 0 or 1, I find that you can show that it's unitary, etc. And and here, for example, I take some state psi, which I just chose the state because it's a state we have worked with in earlier examples in this class. So that's the state square root of 3/2 times 0 plus 1/2 1. And then you can calculate the new psi, which is the psi in the new basis. And you find it's 0.97 and 0.26. And if you go back and look at your notes, or you can verify it yourself by hand, that this was indeed the linear combination that we want. And you can also then do it in terms of the y plus and or plus I and minus I states. Again, define those states, define a new gate which takes you from 1 to y minus and 0 to y plus over here. That's this outer product over here. And then I just have to find the dagger operator over here, which is just conjugate transpose. And then find the new sign by just taking the dot product, that is matrix multiplication of dagger times psi. And that gives me new psi. And again, once you write it out, you can look in our earlier notes, those are the numbers, or I think it's also in your textbook. Anyway, you can verify for yourself that this is all. Anyway, this code will be in the slides, and I encourage you to sort of work through it yourself, like to actually type it out yourself. Because if I just give you the notebook, a lot of times you just won't even look at it, right? So I encourage you to from this code, start playing with it, and whichever language you want, either Mathematica or Python, encourage you to try and work, type it out yourself. Okay. So here is the one more relationship that I want to introduce, which is called the completeness relation. So we recall this projection equation. So what this projection equation is saying, if you remember, is psi on the state 0 has a component. That component is the inner product of psi with 0. That is the projection of psi onto the state 0 plus the projection of psi onto the state 1 times the state 1. Okay, this is just a standard projection relationship. And we can do that for any two orthonormal basis states, right? So we take psi, which is alpha psi times alpha plus beta psi times beta. Okay. So now psi in any basis can be written as projection of psi into alpha times the state alpha plus projection of psi into the state beta. So that's just inner product of psi with alpha, inner product of psi with beta times the state beta. Okay. Everybody okay with this equation? Yes? Yes, if you're confused or don't remember this, let me know. Okay. So now what we'll do a little bit of clever rewriting. This guy over here is just a constant. Because remember, it's like the inner product, it always gives you a number at the end of it. Yeah, and so does this. So I can write it any way I want. I can move it around to that side. Okay. I move it over here and write this as alpha psi. Okay. Plus beta psi. Remember, this is just a number. So I'm allowed to just move it around wherever I want, but it's just a number. We know what happens when we multiply it either to the right or to the left. And now this is very suggestive because this looks like an outer product over here. This part over here. The outer product of alpha and alpha. And this also looks like an outer product of beta with beta. So let me define the outer product alpha plus beta Okay. Well, from this relationship, you can see for any psi, if I call this some gate U, right? Then this gate psi is equal to U times psi. And the only way this is true for every psi is if U equals the identity matrix. Okay. Therefore, we have that if alpha and beta are orthonormal basis states, remember that's an important criterion, because otherwise we couldn't write it like this. We can't write this first equation unless alpha and beta are guaranteed to be orthonormal basis states. But if they are orthonormal basis states, we have just shown that this relationship must be satisfied. The outer product of alpha and the outer product of beta must be equal to the identity matrix. This is called the completeness relationship. Okay, it's like a theorem. Okay? And what it says is that any orthonormal basis state will satisfy this relationship, or a basis state is orthonormal if and only if it satisfies this relationship. Put it that way. The two are equivalent statements. So it's a mathematical way now to check. If you're given to any two states, alpha and beta, you can now just simply, either using Python or Mathematica or doing the algebra the honest way, by hand, then you can verify that it truly is an orthonormal basis state by just calculating these two matrices and adding them up and seeing that they indeed give you the identity. So this is just a way any two basis states I give you now that we can calculate whether they are indeed an orthonormal basis set or not. Okay. Again, it's just some, what do I say, like a theorem. It's a mathematical theorem that's very useful in linear algebra. Okay. So that was a proof. And I had already in the Python code, and a couple of times I had been checking to make sure I didn't make any mistakes, because one of the things that happens is I'm typing stuff in and I make a mistake, right? And this is a quick way to make sure I didn't type one of the basis states wrong or put one of the daggers in the wrong place or whatever, and so, I just quickly check the relationship, I make sure, ket 0 bra 0 plus ket 1 bra 1, right? This is an identity matrix. You see that, okay? Same thing with any complicated one, like these are two new states, plus and plus, okay, I did plus and plus, I could have chosen some other state. And that's something maybe as a homework you can try, plus with plus, minus with minus, the outer products, that again gives me an identity matrix. So that guarantees that that is a orthonormal basis set. And you can do this for arbitrary alpha, beta. Yeah, that's just all of what I just said earlier is just summarized here on this slide. And yeah, I don't have anything more to say on that. Okay, so before I move on to the next step, any questions? I know it's a lot of math and stuff coming at you. Don't hesitate. Yes.
You learn about things that are orthonormal.
Yeah.
There are things that there's no interest and there are interest later on.
Are they of interest if they are not orthonormal? That's a good question, actually. I think it's something like, about Fourier transforms, right?
Sometimes.
Okay. So it's like saying, why do we choose cosine? If you all know Fourier transform, like everybody heard of them vaguely? Okay. If you know that any function f of x, the Fourier theorem says, can be written as some combination of cosines and sines. Why did they pick cosines and sines? Okay. Why not some other function? In fact, it can be made into other functions as well. It's because cosines and sines, in some sense, form an orthonormal basis set. You can prove the same theorems for Fourier using this ket language, but just translate it to higher dimensional spaces. There's the same algebra, exact same. You have to define a new inner product with integrals rather than dot products or complex matrix operations, but the exact same idea. So why do we pick cosines and sines? For that reason, and the same reason in quantum mechanics. Orthonormality is just this beautiful property that helps us to calculate all these coefficients really easily. Now, could there be interesting basis states that are not orthonormal? I think so. I mean, I think like when you get into more complicated systems, which are not closed quantum systems, open quantum systems, then it turns out that what happens is that states don't just live on the surface of the Bloch field. They can go inside the Bloch field, for example. And now you may start to get evolution into systems that are non-orthogonal, and you may have to, worry about that. But usually the way we describe that motion isn't by decomposing it into any complicated motion, we decompose it into the coefficients along the orthonormal direction, something of that nature. But it's a good question. I have thought about that actually, because there may be some interesting dynamics and stuff that happens if you choose non-orthogonal directions. Anyway, okay. Any other types of questions on this? So in the last maybe 10 minutes of the class, I wanted to go over quantum bomb detection again, but I don't want to go on unless I know that everybody's feeling comfortable with the material so far. Because now we're going to start putting it all together in a more, cohesive way, but it's also more, you have to follow along all the steps as we go here. If you don't follow every step, we can always go over it. Okay, so again, I recall to you the Elitzer-Weidman bomb problem. So there was a box with a bomb in it and a Turing machine. I say Turing machine, you can think of it as a detector, you can think of it as, a single bit computer, whatever you want. It's just a computer that just, if it gets a 0, then nothing happens to the bomb. If it gets a 1, it explodes the bomb, right? That's the basic idea, okay? And then there are some of the boxes that are Dutts, right? Where the state that you send in just comes out on the end, nothing happens to it because the computer is missing, whatever, or you want to think of it, it's broken, etc. And the bomb does not go off. It's a Dutt bomb or a Dutt box, okay? And so we don't know which of the boxes, there are many such boxes, and we don't know which of them are working and which of them have Dutts. And of course, we want to find the boxes, but not detonate the bomb, because the bomb, if it detonates, then we have shattered box, nothing useful left for us after that. And possibly we are also dead. So this, if you recall, so in classical computing or classical physics, whichever way you want to think about it, there is really no way to solve this problem. If you go back to the result over here, if I send in a 0, in the two cases of a dud or a bomb, I get an output 0 and no explosion, but I can't tell which one is a dud and which one is a bomb. If I send in a 1, well, it comes out in these cases, 1 comes out, but in this case, it explodes the both ones. And those are our only two choices in the binary logic or in the classical logical world, right? There's only two choices. So Kadira, our heroine of the story, if you remember, sent in a plus state, and half the time there would be an explosion because a plus state, as you know, is 1 over root 2 0 plus 1 over root 2 1. And so it has a 50% probability to be detected as a 0, 50% to be detected as a 1. But if there's no explosion, the trick, right, is that we can actually differentiate between the dud and the bomb case by measuring in a new basis, the plus or minus basis. Because nothing happens to the bomb, to the state qubit, the qubit state, which is in the plus state. If there's no explosion and it goes through a dud, it remains in a plus state, right? Okay, so that could be a dud or it could be a bomb. Okay, just means that we don't know. But if we get a definite no, that is, it's in a minus state, then for sure we know it was a bomb. Okay, but the problem, of course, was the statistics was pretty bad, right? It's 50% of the chance we get an explosion. And this is just the same logic I laid out for you in an earlier lecture, just repeating it over here. Okay. Oh, and the reason that even if there's no explosion is, remember, the Turing machine measures in the 0 or 1 basis. So when it measures in the 0 or 1 basis, there's a half probability that it gets a 0, right? And that's fine with us because 0 is safe for the bomb. Okay, it doesn't explode the bomb. But then when we measure it again in the plus or minus state, we have 50% chance of getting plus, 50% chance of getting minus. That's the reason we get this statistics in the end. Okay. All right. So in the end, we had a 25% chance we can detect the bomb versus that, which is an improvement of infinity over the other case where we had no chance of detecting bomb versus that. But still, it's only 25% of the cases. So that's a small probability, and we would like to make this probability bigger. And now we will show you how to do that using the language of the linear algebra that you have learned. Okay. Yeah, so now that we know about linear algebra and gates, let's define a new, the basic idea is actually somebody, I forget, somebody out here had kind of asked this question back when we were talking about it, is what if you don't rotate it into the plus and minus basis? What if you rotate by a little bit? And that's exactly the idea. We're not going to use a basis of plus and minus, because plus and minus, let me just show you here. So remember the block sphere, our old friend, and you must be very familiar with it now after the homework, I think. So 0 and 1 is our states on the block sphere, and plus and minus are these states over here along the x-axis. So you can see on the block sphere, they're rotated by 90 degrees from the original axis, 0, 1 axis, to the x plus x minus x axis. What if we didn't rotate all the way by 90 degrees? What if we rotate only a small amount? And that's the basic principle of this approach. So we define a new orthonormal basis set, U and V, and we know how to make that rotation gate for this new state, any two states U and V, as long as they're orthonormal, we just write out our rotation gate in exactly the same way as we did for the plus and minus states. Okay, this new R gate is U0 plus V1, and it tilts the axis a little bit. So these are our new states, U and V, which are our new basis states, and they're opposite on the block sphere. Yes?
Really close to the one state anyways. Would we not load the working bombs as we're sending stuff in? Because we're already like really close to one.
No, we start in 0, remember?
Okay.
So when we start in 0, we'll be we'll be in the U state.
Okay.
Well, yeah, I'll show you the protocol in a minute. I just wanted you to understand the basis states even. Okay, and here is the state U and V. I'll show you how you got these states using the language of qubit gates. But you can see it's like if epsilon is small, okay, epsilon is a small angle, then cosine epsilon is almost 1. Okay, sine epsilon is almost 0. So this is almost 0 plus a little bit of 1. And same over here, this is small bit of 0 with mostly 1 over here. So U and V are close to 0 and 1, but not quite. They are slightly tilted. Okay, everybody okay with this so far? With these new states? And actually, I'm going to say that epsilon is an integer fraction of pi. Why you'll see in a minute. Okay, let's call this epsilon equals pi over n, where n is some number that we choose in our protocol later on. Okay, some integer. Okay, just to show you how I got that gate, that earlier expression over here, this one over here. Recall that 1 qubit quantum gates, the most general 1 qubit quantum gates, are rotations about any axis by an angle theta and can be written in terms of I, X, Y, and Z. Okay, we proved this result, or we postulated this result. I'm not going to prove it to you because you need some higher mathematics for it. But the point is that any gate U can be written as this combination around any axis X, X, Y, Z, can be written as this equation. Okay. But now remember, in the language of linear algebra, I, X, Y, and Z are just matrices. Right? So all this is taking some matrices and adding them together with some angle. So let's do that with the angle epsilon. And actually, so before I do that, let me just go back a little. We can see from the geometric picture, if U and V are slightly tilted and they remain in the XZ plane, that means that U and V are rotations around the Y-axis, right? We take this line along the Z-axis, tilt it slightly over to the left or anti-clockwise around the Y-axis, right? It tilts over a little bit to the side. That's just the intuition, the geometrical picture. You don't need to rely on it. You have this formula over here, and you can just plug in and verify that indeed that gives me that matrix that I just wrote down for you. So we will do that here. Okay. How about this? I don't have time to go through the math of this at the moment. Why don't I assume the math for now? We'll come back to the math in the next lecture. The math is just plugging in for the matrices I, X, and Y, and Z and doing the math. Okay, it's not very difficult. So just remind me in the next lecture that we'll go through it and we'll go through it. Okay? That's just a calculation, but here's the protocol. Okay. So now I'm going to send in not the state 0, but the state U. Okay, so which is 0 rotated by around the Y-axis by that small amount epsilon. Do I get an explosion? Then of course I'm dead. Okay, it's over. But if I don't get an explosion, I rotate again. That is, I rotate by the same operator, R, okay, which I constructed in that earlier slide, which is just again another matrix. Again, we do this n times. Remember that n that I picked, the n fraction? And then at the end, I measure in the UV basis. So along those lines, U and V. And my claim is if I get 1, it's a dud, and if it's no, it's a bomb. This looks very much like Kadira's previous protocol with plus and minus, except now we have called around this new basis set U and V, and we have rotated n times in this loop. Okay. So let's go through the protocol. Okay. So remember, when I send the qubit through a gate R dagger, if the result is before I get into it, I wanted to point out how do I measure in some new basis. So when I measured along the plus and minus basis, you know what to do. You just project it onto the plus and project it onto the minus. Same idea. I want to project onto U and V. And the way to do that, as I've shown you earlier, is simply take the qubit and multiply it by R dagger. Okay. Whenever I multiply by R dagger, if the result is 0, right, I measure 0, it is in the state U. And if the result is 1, it is in the state V. Just the same idea I think we had written over here. R dagger is the state side. So it's basically like doing again that inverse operation that I was telling you about. So we basically want to project it along the state U and V rather than along the state 0 and 1. That's because R dagger acting on U is 0, R dagger acting on V is 1. Okay. So, okay, again, I have to come back to this math in the next class. So let's verify it for the X basis. Okay, we've kind of already done it a couple of times, but we'll do it again, just take it on faith that this is indeed true, right? So here's the protocol. We apply R to the state 0 to prepare U, which you can do, for example, in Quark or just in Python or any other language. Okay. If it's a dud, nothing happens to the qubit, right? The qubit just goes straight through. It exits. This is one round of that loop, basically. Okay, I'm just doing one round of the loop. That is, we don't loop at all. We just take it out. Okay. Exits with the same state because it's a dud. So we measure in U. Remember, we sent in U, okay, and nothing happened because it was a dud. So if you measure in U again, I'm going to get U. I'm going to get the state U with probability 1, right? Okay. But if it's a bomb that's in that box, then the bomb measures the state U along and finds a result, either 0 or 1. If it's 0, we are fine. If it's 1, it explodes. Okay. So the safety is when it measures 0. And remember, our state U is close to 0, so that probability is cos epsilon over 2 the whole square, which just comes from the construction of the state U. And that's almost close to 1 because epsilon is small, cos epsilon over 2 is 1. So this is close to 1. You can expand it, but it's basically 1. Okay. What about the probability of explosion? That's what we want to avoid. Well, the probability of explosion is we measure 1, which is sine epsilon over 2 the whole square. For small epsilon, for sine epsilon over 2 is just epsilon over 2, just an Taylor expansion of sine. Okay, sine x equals x to first order, then higher order, x cubed, etc. So that's approximately epsilon squared over 4. Everybody with me so far? We're just going to repeat this protocol n times. That is, if we don't get an explosion, we just send it back, multiply by r, and repeat n times. Okay, so let's go through that. Well, if it's a Dutt, that state each time rotates by an amount epsilon over 2. Next time it rotates by another epsilon over 2. So now the total angle is epsilon. Then 3 epsilon over 2, etc. After n, it is basically n times epsilon, which the rotation is by an angle epsilon, not epsilon over 2, because that's how the gate was constructed. Okay? So each time it rotates by an angle epsilon. So after n times, it will be n times epsilon, but epsilon is pi over n. So that's a rotation of pi. So 0 becomes 1 after n rotations. So now if I measure in the UV basis, the final state will be V with the probability 1. Okay. But what if it's a bomb? Okay. Well, if it's a bomb and there's no explosion, okay, then the Turing machine measures the qubit, finds 0. Okay. Each time, so the output state is 0. Because otherwise, if it measured 1, there would be a problem, it would explode. So when it sends a 0, if you go back to the protocol, every time that there's no explosion, the Turing machine has measured a 0, I've sent it back here, so I do a rotation, I get back the state U. I don't get U rotated each time, I just get U each time. Because I got no explosion, the state must be 0 coming in here. It's like I started the protocol right at the beginning. So when I rotate here, I have sent in again the state U and not the rotated version. Okay. So that just brings us back to the probability, which is that it is the qubit resets to 0 and is rotated back to U again. So the probability, of course, is still 1 every time, close to 1 every time that there's no explosion. Okay. But what is this? But this adds up, right? If you do n times, each time the probability might be small that there's an explosion. But if I repeat it n times, the probability obviously increases. It's like flipping a coin, right? If I have a small probability, let's say, or some other event, like the small probability I'm struck by a meteor and killed right now. But if I multiply this by like billions and billions and billions of people and billions of planets, then on some planet somewhere, some version of me is getting killed by a meteor right now, right? So same thing. So if I measure what's the probability of this explosion, then epsilon squared over 4 is the probability of one event that there is an explosion times n, the number of times I repeat. But epsilon is pi over n. So this goes as pi squared over n squared times n, so pi squared over 4n. Okay. But pi squared over 4n is just basically 2.5 over n, approximately. Okay. And that goes to 0 as n gets larger. So if I pick n large enough, I can make this probability basically go to 0. So, just as a quick calculation, if I set n 1,000, then probability of an explosion goes to less than 0.25%. So we went from 25%, which was the case when we chose the plus state, to less than 0.25%. So this is how we can make a more perfect quantum bomb detector. I know that went by fast, so we can go back over it again in the next class and we'll finish up some of the calculations. All right, I'll see you all on Friday. And if you have any questions, yeah, just feel free to ask.